Okay, then hello everyone. Welcome back to our Wednesday seminars. So today we have Rafael Mancini Santos as our speaker. Rafael graduated in computer science from UFLA in 2020. He did his master's in physics from UFLA again in 2022. He is currently pursuing a doctorate in astrophysics from INPE Sao Paulo. He is interested in general relativity testing, general relativity test using gravitational wave data, statistical inference algorithms, semi-classical gravitation, and quantum field theory and optimization algorithms. So today he will be discussing with us gravitational wave astronomy as a probe for novel tests on general relativity. So let's welcome Rafael. Okay.
Oh, so thank you. Should I start?
Yes, yes.
Okay, thank you, thank you. So good afternoon, everybody. Uh, yes, I'm Rafael Mancini Santos, and today I'm going to talk a little bit about the works that I've been doing with my supervisors, which are Rafael da Costa Nunes and José Carlos Neves de Araújo. And the title of this presentation is Gravitational-Wave Astronomy as a Probe for Novel Tests of General Relativity. So yes, without further ado, let's move on. So just to give you an overview of the presentation, I'll start as usual with an introduction about the subject. Then I'll talk a little bit about the theory behind gravitational waves. But yeah, it will be a really brief talk about the theory. Won't delve too much in detail about the theory. But then I'll move on to tests of general relativity using gravitational waves. And as examples, I'll talk about the works that I've been doing with my supervisors during my PhD. And then to wrap it all up, I'll try to give some final remarks about some future perspectives of the field and all that. So just, yes, to start, like just to give a brief history, really brief history of gravitational waves. And yes, this all starts with the seminal work published by Albert Einstein about 100 years ago, in which he proposed the general theory of relativity, with reimagined the gravity, which was thought to be a force field, as proposed by Isaac Newton, as curvature of space-time. And space-time itself is also another thing proposed by the theory, because before space and time was thought to be different things, and now space-time brings those concepts together as different aspects of the same thing. So a direct consequence of that is a phenomenon which was called gravitational waves, which can be described as ripples in space-time, as is usually said in pop science things. And maybe a useful way to think about them is like to make an analogy with electromagnetic theory, because when you perturb an electromagnetic field, you get these perturbations propagate to infinity, and we call them light or electromagnetic waves. And the same thing happens to gravity. If you perturb it strong enough, these perturbations can propagate to infinity. And this phenomenon went without evidence until after the discovery of the Holst-Taylor binary, a neutron subbinary containing a pulsar. And the thing is about this binary, they were able to measure very precisely the orbital period of this binary and how it evolved over time. So by doing these kind of measurements, Holst and Taylor, for about 30 years or so, they were able to verify that due to gravitational radiation, as predicted by general relativity, the orbital period of the system would decay over time as the orbit shrunk. So their measurements matched exactly the prediction of general relativity, which won them the Nobel Prize eventually. And going forth some years into the future, we had the first direct evidence of gravitational wave. Because yeah, I didn't tell, but that was an indirect evidence. Then we had the first direct evidence of gravitational waves, which was a gravitational wave signal detected from the merger of two black holes of about 30 solar masses each. And the smudge on the middle of the plot is like the signal, the what is called the chirp of the gravitational signal, because there's this tendency of these merging systems that the frequency of the gravitational waves tend to increase as the system gets closer to merging, and then it just goes all the way up and does like a chirp of a bird or something, if you translated the gravitational wave signal to a sound. So yeah, and it is amazing to think that just 10 years after the first detection, we got a very similar gravitational wave detection coming from a very similar system. uh, Again, a system of two, a binary of black holes of 30 solar masses each, more or less. And the signal that was detected now is so much clearer than what was than the first detection. And it was basically just the technological improvement of the detectors that were made during these 10 years. And it is incredible when one just looks at what we are able to achieve today due to this technological advancement of the detectors. This is a plot of the constraints on the masses of the black holes of the system that emitted the gravitational wave signals. And just in 10 years, we got a huge improvement on these constraints. So this not only I think it's amazing by now, but it gives us a lot of hope for the future, for and particularly considering tests of general relativity, which is the thing I work on, and which I'll talk a little bit more later. So yes, to talk about the current state of things, we have more than 200 gravitational wave signals detected by now, and this number is increasing by the day. This is considering the last batch of detections that were released by the LIGO team, which the first part of the fourth observational run. So, and it is expected so by the end of the fourth observational run, that we maybe get like 500 gravitational wave detections or something of the sort. I can't remember that exactly. So yeah, one could ask at this point, but why? What is so important about gravitational waves? Well, the thing is, just there are a lot of things really important, but to give a really brief statement about the importance of these things and to focus on the things that we are able to detect now. These gravitational wave signals come from extreme gravity systems, a system that in which the gravitational field is really strong and dynamical. So, like merging of two black holes, this can tell us a lot about their paths that black holes can take to form the ways that black holes can form, and they can tell us a lot about their properties too. So, or maybe even reveal, hopefully, new properties in the future. We don't know, but that is a possibility. Concerning like neutron stars, they can gravitational wave signals can tell us about the state of matter inside the neutron stars, since they have a internal state. Um, they can maybe help us build better equation of state. And there are a lot of more possibilities that are related to future detectors, or maybe generation detectors, like um, gravitational wave signals coming from the early universe, are coming from different astrophysical sources like supernovas, or maybe even less extreme compact objects like white dwarfs, brown dwarfs, and all that kind of thing, which are things to be thought about in the future, or maybe not, but just to prepare. So yes, about general relativity, all this is based on general relativity. So which is summarized by this. Yes, this is subjective, but this I think is a beautiful equation. And but yeah, general relativity, as successful of a theory as it is limited, and its limits are pretty well known by now. At its core, and for starters, it predicts singularities, which are basically just failures of the theory to explain certain regimes, like the center of static black holes. So, um, and related to that is the fact that we still don't have a quantum theory of gravity, and um, that gravity, as it is described by general relativity, is incompatible with quantum theory. Also, general relativity needs a dark sector to explain some observational phenomena like the dark matter and dark energy. So yes, it's still an incomplete theory of gravity. There must be more things to be revealed yet. And in this sense, there has been a lot of work in proposing different alternative theories for gravity. And there's this thing, this lovely theorem called Lovelock theorem that says that if you want to modify general relativity, you must introduce new degrees of freedom. You must at least you introduce some extra fields, some higher dimensions, higher than 4 dimensions, which is the number of dimensions of general relativity. You must um, violate like the symmetries of the theory and all that. And there is a lot of different alternative theories of gravity, and they all can be eventually tested using gravitational wave signals. And the thing is, general relativity has already been thoroughly tested in the past, and we can divide these tests that were made by the how strong and how dynamical the gravitational field is in these regimes that were tested. So just give an example. Concerning solar system tests, this is a regime where the gravitational field is very weak and static, basically. So, and a lot of tests have been done in the past, the solar system concerning this regime of the solar system, and general relativity has been really successful in that. There are tests concerning like binary pulses where the gravitational field can actually be strong, but it is still not very dynamical. And there are gravitational waves which probe uh, regimes where the gravitational field is very strong and is also very dynamical. So gravitational waves gives us a glimpse of a regime previously unexplored uh, of gravity. So yes. Now to talk a little bit about gravitational wave theory. First, I put it that way because maybe not everyone has studied or is working on general relativity. So in general relativity, the basic dynamical variable of the theory is the metric. It's called the metric, and it's usually represented by this mathematical symbol over here. And it is basically a function that tells the interval between two events in space-time. And when we say that space-time is flat, when gravity is absent, we call that a flat space-time, and it is usually represented by this other mathematical symbol here. So, a basic way to start considering, to start to understand gravitational waves is to talk about perturbations over flat space-time, linear perturbations over flat space-time. So that would be mathematically represented by this equation on the screen. So just adding a linear perturbation over a flat space-time. And with this simple model, also called linear gravity, one can learn a lot about gravitational waves, at least some fundamental aspects of it. And one direct thing that one can learn from this simple model is that gravitational waves have two main kind of polarizations. One is called the plus polarization, which is represented by the plus signal, and the other one is called the cross polarization, which is represented by the cross signal, of course. And this equation 3 in the screen is just like a basic solution of this simple linear model that can describe the gravitational wave. So one way to think about these polarizations, these different polarizations, is to think would they affect a ring of test masses? And the picture on the screen illustrates that. If you think of the screen like a Cartesian coordinate system, a Cartesian plane, the plus polarization would affect it like that, parallel to the axis of the coordinate system, and the cross polarizations would like deform the ring in the diagonals of the system. And that is important, will be more important when I talk about the detector of gravitational wave. But I'll return to that. But then, yes, this is a simple model. This can already tells us a little bit about the gravitational wave, but the real profile of a gravitational wave is much more nuanced than that and cannot be described by the linear theory. And actually, it also depends on the source of the gravitational wave that you are considering. And I would like just to show you the main source that is being at least discussed right now, because it is the source of gravitational waves that can be detected by the LIGO team, which is the gravitational wave coming from the merger of compact objects, like the merger of black holes. And the profile, the gravitational wave profile from a system like that can be divided into three phases. The first is the spiral phase, which concerns when the bodies are really far apart from each other. So the physics there is basically Newtonian. It's not actually Newtonian, but it can be described by a framework which is called post-Newtonian expansion. So it can be like analytically treated, more or less. So, and it is like a more well-behaved part of the gravitational wave signal. But then as the bodies come closer together, uh, the gravitational field will eventually start to get more complicated, and we get to the merger part of the signal when the bodies like plunge into each other and merge. And this is the really complicated part. This is usually treated using numerical relativity. And after the bodies may merge, in the case like of black holes, the remnant would be like a deformed black hole. And these deformations that comes from this post-merger, they are radiated away uh, in a manner that if you translated the signal to sound, it would sound like the ringing of a bell or something like that. And that's why it is called like the ring down part of the signal. And this is usually treated using black hole perturbation theory. Um, each part of the signal can give like different information about the system. So, but yeah, it is, each part can be a presentation for in itself. But the thing is, when you consider like neutron star binaries, which can have which have internal structures different from black holes, then the internal structures of neutron stars will affect the gravitational wave profile too. So not the profile, but it will affect the gravitational wave signal, particularly the phase of the signal. So that if you consider neutron stars with similar masses than black holes, you would actually have the merger happening sooner than compared to the black hole part of things. So yes, this is just to illustrate this difference between black holes merging and neutron stars merging. And okay, so yes, how are gravitational waves detected after all? So the basic detection apparatus that is used is the laser interferometer. Uh, the architecture of the detector is basically illustrated by this image. You have a laser, and the laser beam goes to a beam splitter, and you have these beams being separated like perpendicular to each other. Each one goes to an arm of the interferometer. These laser beams are then reflected on these mirrors, which they then come back to the beam splitter, and they are combined in the receptor, the photoreceptor over here. And the thing is, it's cool that there in this picture there's the name test masses here attributed to the mirrors, because we can think about how this kind of thing can detect gravitational waves by looking at how at this image that I already showed you before. um, uh, by looking how the gravitational wave, the different polarizations of the gravitational wave affect a ring of test masses. So it's basically like that. Because of this deformation that can occur when there is a passage of a gravitational wave, the movement of the test masses will dephase the two laser beams, so that when they recombine at the photo detector, they will have a phase difference, and this phase difference can be then translated into the gravitational wave signal. But the thing is, yeah, I would really like to have an animation right now, but I'm using Beamer I use Beamer to do this presentation. But okay, let's move on. The What can could calculate the optimal arm's length for such that we get a good detection. Uh, so that would be like an unfeasible thing to build, but people can get smart about it and just build a smarter design, which is like illustrated by this other laser interferometer that is called the Fabry-Perot detector. And to circumvent this need to build longer arms, one thing you can do is you can make light travel a longer path in a smaller arm, and the effect is more or less the same. You make light bounce in a arm a lot of times so that it travels a longer path, and then you have more or less the same effect. But the thing is, um, if we consider, as it happens with any detector, the signal that will come out of the detector will be like the true signal plus the noise. The thing with gravitational wave detector is that the noise is much higher than the signal, and uh, was a huge challenge for people to figure out how to make the detection work. So the thing is, the strategy that they use at LIGO is to try to match the signal. They actually they need a noise model. They have yeah, a very good model of the noise that they will have in the detectors. And uh, in spite of that, they also, no, not in spite of that. Uh, Uh, with that, they also have a template bank, a database of different gravitational waveform templates. And they have a algorithm that is called matched filtering, in which the algorithm searches in this database for the waveform template that will best match the signal observed in the detectors. So the detection itself depends a lot on how well you can model a gravitational waveform. So that's the main thing. Now, once you get the signal detected and you have it all, you have post-process it and all that, you can do the gravitational wave data analysis. And the main concern would be like to check if a particular model will fit the data or which model fits the data best, which is basically like what you do with a template bank of waveforms. And yeah, different GR models, general relativity models. In this case of template banks, they're called waveform approximates. Each waveform model is called a waveform approximate. They differ by how detailed are the model of the waveform, if like they consider that the spins of the system is aligned or not, or they precess or all that kind of thing. And another thing would be to consider different general relativity models to see which one fits best the data, and one could consider different modified gravity models, or maybe introduce parameterized deviations from general relativity. And the main tool, statistical tool to do that is Bayesian inference, which basically works like that. If at first you assume that a specific model, and you assume that the parameters that describe this model are random variables, and then you start with some expectation about these parameters, which would be like, since they are random variables, you assume that there will be distributions, and this is called the prior distribution. And then you must also have a likelihood, would be like a function that tells you how well these parameters given this model matches the data that you have. So that the data can inform you which parameters are best. And then when you combine your prior expectations with this likelihood model, you then get your estimate, which is called the posterior. Uh, and this is basically summarized by the Bayes rule, but which is given by this equation on the screen. And one could even ask, why not calculate the likelihood for every possible outcome? Well, maybe this can be obvious by now, but if we consider a a system like a binary black hole system, uh, the least amount of parameters they can have is like 11 parameters. So you have the intrinsic parameters of a binary black hole system, like their masses and their spins, if their spins are aligned, if they are not. So you need three components for each spin. And you have the extrinsic parameters, which will tell like the distance between the system and the Earth, or the localization of the sky and all that. So the parameter space of such an analysis is really big. So you cannot just evaluate a likelihood for every possible outcome for these parameters. It suffers what is called the curse of dimensionality. So what you must do is to rely on what is called stochastic samplers. You try to sample randomly from your estimate, from your posterior distribution. And a very well-known algorithm to do that is the Markov chain Monte Carlo algorithm, which is basically like you start with a sample from your prior distribution, and then the algorithm proposes new samples based on a proposal distribution. There's a lot of technicalities in there. And the goal is to wherever you start from your prior distribution, you eventually end up drawing something like something that will resemble your posterior distribution. So the thing about the algorithm is you must tune it correctly so that it focus on this region that the likelihood is higher. So okay, there are Python libraries to that implement this like the Markov chain, Monte Carlo algorithm, and a lot more different stochastic samplers. The main ones that are used in this field are there's one called Bilby, and the other one is called PyCBC. And now I'm trying to talk a little bit about the testing general relativity now, given that I at least try to talk about the statistical tools and the things, the gravitational wave theory and all that. Now to the testing part. Just to remind you that there are a lot of different alternative theories to gravity. Um, but it will be such a maybe it will be hassle to maybe pick each one of these alternative theories to test against GR, given gravitational wave data. So there is a nice framework which is called the parameterized post-Einsteinian framework, which enables one to map different alternative theories to gravity to this to some theory agnostic parameters, which are then implemented into a waveform model, such that when you test your waveform model, you can establish constraints to these theory agnostic parameters, which are then translated to all these different alternative theories parameters. So, but you can do the other way around too. Sometimes it's easier to just map take a particular alternative theory of gravity and map its influences on a gravitational wave signal through this parameterized Post-Einsteinian framework. So the basic waveform of this thing would be like the equation on the screen. Uh, these parameters that have these PPE parameters here are the theory agnostic parameters. The alpha and the A here controls like the deviations from the amplitude as predicted by general relativity, and the beta and the B parameter here controls the deviations from the phase as predicted from general relativity. And now to give examples, there's this first work that we did during my PhD, which was considering a model that introduced a parameterized deviation of general relativity, and that is mainly just you pick uh, a solution of general relativity, like the Kerr solution, which is a well-established thing, and you introduce a deviation from this solution controlled by at least one parameter. So when we talk about parameterized deviations, there doesn't need to be a fundamental thing to this. It doesn't like different from modified gravity theories, which usually comes from like an effective field theory from string theory or something like that. When you talk about parameterized deviations, you're talking about a more pragmatic approach. But at the same time, you don't if you find some constraint to this deviation parameter, you usually can't map this constraint to a particular physical thing. So yes, you can map it to the theory agnostic parameterized post-Einsteinian parameters and then map it to specific modified gravity theories, but that is another thing. Um, but they are simpler to test. And we did that just to give a sense of the modification that are introduced to the gravitational waveform. This is a plot of a simulated gravitational waveform comparing different values for this deviation parameter with general relativity, concerning the time domain waveform and its amplitude. And we ran a Bayesian inference on this using this model. And what we found, what is usually the case when testing general relativity, we did not get any deviations from general relativity. It, and then we did another work. Uh, in this case, we picked a specific modified gravity theory, which is called the Lumno-Horndesk theory, which is a subclass of the Horndesk theory in which the speed of the propagation of gravitational waves matches that of the light, which was a constraint put by a seminal detection, the detection that occurred in 2017 of a binary neutron star, which was the first and only multi-messenger detection. Yeah, I should have put it in this presentation. But nevertheless, this theory can yield hairy neutron star and black hole solutions. And what does it mean by hairy? It means that there can be extra properties, extra properties that are beyond general relativity to neutron stars and black holes. And these properties are associated with the coupling of an extra field. In this case, it is a scalar field to gravity. So, like stars can get a scalar charge, which is associated with this coupling of the scalar field to the gravitational field. And this can alter the gravitational wave signal to give, this can have like a imprint on the phase. There is a phase difference when you compare the signal to what would be predicted by general relativity. And yeah, we run some analysis using neutron star black hole mergers because we were focusing on the possibility of constraining the presence of a scalar charge in neutron stars. But the results all agree with general relativity. And finally, there's a work that we uh, submitted this year, and it's in a different path than the previous works that I talked about. It recently got accepted, and what we did is because there is the possibility that neutron stars can accumulate dark matter. So, and one can model the accumulation of dark matter inside neutron stars as through the what is called the Tove equations, which is basically a solution of general relativity when you consider the presence of matter, and particularly if the matter is a perfect fluid. So in this case, consider a neutron star as composed of two perfect fluids. And the Tove equations in this scenario would be given by these two equations, the 11 and 12. And one fluid would be like the baryonic matter, and the other fluid would be dark matter. And in this case, it's a specific model of dark matter. It's a self-interacting bosonic model. Um, and it can affect the gravitational wave signal through what is called the tidal deformability, which is basically a parameter that measures how much the internal structure of the neutron star is deformed by the presence of another gravitational field, of the gravitational field of a companion star in the binary. and this can have consequences uh, because, yeah, as we would expect, um, the presence of a different these alteration of the structure of the neutron star will change the orbital energy, which will change the gravitational waveforms. And the effect of the presence of dark matter inside neutron stars, depending on the fraction of dark matter inside neutron stars, can have, and depending on the mass, they can have different effects. This first plot on the left considers um, more heavier particles of dark matter of this self-interacting bosonic model. And if particles are heavier, then the higher the fraction of dark matter inside the neutron stars, the less the maximum possible mass these neutron stars can achieve. And if you consider lighter particles with a smaller mass of dark matter, then the higher the fraction of dark matter inside these neutron stars, then the higher the maximum possible mass they can achieve. This is because there are two possible regimes that that can occur in this model that we consider for this work. One regime is, which is represented by this plot on the left, is when dark matter concentrates in a core inside the neutron star, as a core inside the neutron star. And the other regime would be when dark matter concentrates as a halo, more outside the neutron star. So it also, as one can see in this plot, it also extends the radius. This radius is like the sum of the radius from baryonic matter with the radius from dark matter. So this is why the radius can get too high. But if you consider just the baryonic radius, it will be like more closely related to the plot on the left. And but the effects, if you consider just the effects of tidal deformability alone, the effects are really small because the tidal deformability effects coming from this tidal deformability are effects that uh, occur just at the late in spiral phase when the neutron stars are really close to each other. So, did someone say something?
No.
Oh, okay, sorry. So it's a small effect, but the thing is, as you saw in this plot, in these plots here, it can have great effect on the mass, on the possible masses of a system. So what we did, we established a strategy where we consider also the effects that this could have on the masses of the system, and the results from this work were uh, we try to constrain these parameters associated with the dark matter model. So the mass of the particle is here, this is a coupling constant, and then this is the fraction of dark matter inside neutron stars. So yes, there's still the signals that we have now are still too weak to properly constrain the microphysics of a particular dark matter model by using just gravitational waves. But this work actually gave us some insight about how could one do that once we get better detections, and also uh, uh, how are the effects or the biases that one can get using this kind of approach concerning all the analysis. And uh, just to give some final remarks, um, yes, we have future ground and space-based detectors that are currently uh, that will be built in the future, and they may offer a lot more data on this kind of on gravitational waves. Uh, New and because of that, new and faster frameworks for Bayesian inference must be developed and are being developed. Some are even using machine learning techniques and this kind of things to because these tools they are really they use a lot of computational resources. So the better we can make the faster we can make these algorithms, the better. And we should improve the theory agnostic framework so that more tests can be done, novel tests can be done. I just highlighted that too because that's something that I'm working now, but I think my time is already over. And yeah, there is plenty of space to enhance current waveform templates because those will be needed to considering these future detectors. So yeah, that's it. Thank you for the presentation, for the opportunity. And yes.
Thank you. Thank you very much, Rafael, for the amazing talk. So let's take some questions from the audience. Yes, ma'am.
Thanks, Rafael. Very nice talk. I learned a bit about it.
Can you come here?
Can you hear me?
Yes.
Yes. Yeah, my question is, yeah, you said that there is dark matter. Hypothesis that dark matter would accumulate in neutron stars. I wonder why, if this is something particular of neutron stars or dark matter, you could do this test in other gravitational potential, like, dark matters in black holes, dark matter in normal stars, or, white dwarfs, things like that. I wonder why, in particular, the neutron stars.
Oh yeah. Thank you for the question. It's actually just because we wanted to choose this particular model, but there is actually the possibility that to do tests like that using like black holes. It was there is actually a work that was done by I think Nicolas Yunes and his team that they tested a different model of dark matter in which dark matter would like have an effect on black hole binaries. Was like a model of dark matter that included long range interactions between the dark matter and they could accumulate in I don't remember exactly, but they could accumulate. I don't know if in the whole orbital region of a black hole binary system or just around the black holes and they could interact uh, with a long range thing. But yes, there are different models that can be tested in this sense that you said. But yeah, we chose to use this model of dark matter accumulating inside neutron stars.
And the observational signal would be like if we had all the wave pattern, if we could measure precisely, then you could see a shift in phase, as you said. Is that?
Yeah, I don't remember if in phase particularly, but this case of binary black holes with a kind of a dark matter field in there will be yeah. If, I don't know exactly how that different model affects the gravitational waveform, but um, there would be signatures of the presence of this model of the sky, this type of dark matter in there, because the presence of dark matter in the black hole binary system would alter the orbital energy and all that, and you could actually detect this thing in the gravitational wave signals. But yeah, I just don't remember the details because it was I read this work a long time ago.
Okay, thank you.
Any other questions? Yes.
Can you listen to me?
Yes.
So I have a question about the theory that you first mentioned in the last part, this parameterization post-Einstein theory. I wonder if this theory is based on first principles, I mean an action, or what is it based on? And the other thing that I want to ask is if you can explain a little bit more about this mapping that the theory makes, please. Thanks.
Okay. Thank you for the question. No, yeah, I didn't explain it very well by the end of the presentation. That's the thing when I left my phone open with a chronometer here, but I got some messages that messed my head a little bit. But yes, the thing it's not a theory per se. It's a framework where you can map different theories into the gravitational wave form. So if you were asking me about that, it's not like you can uh, get this waveform from an action and then you solve the equations of motion and you derive the waveform by some like post-Newtonian thing or something like that. It's just it's a he proposed this kind of waveform as a post hoc thing, and you can and I don't know if I can answer your second question very well, but yeah, there is like a specific procedure. There's an algorithm where you can take a theory, a modified theory, for example, and if you can calculate like the the radiated energy or the if you can get some information about the orbital dynamics of the theory and all that, you can then use a specific algorithm there to map your theory's parameters to these theory agnostic parameters here. So yes, there I just can't I think explain to you really well this part.
Thank you.
Okay, now let's the questions from the online people. Horacio, you can ask your question.
Yes, did you hear me?
Yes.
Hello?
Yes.
Oh, hi, Rafael. Thank you very much for your nice talk. Very interesting. Would produce any difference in the heavy element produced during the merge of black hole with a neutron star or neutron star, the different models? Or you didn't talk about the heavy element production during the merge.
Oh no. And I actually I'm sorry, but it's not something that I have like studied. So I can't I don't know how I can't say
Okay.
anything about that
Okay.
properly.
Thank you.
Okay, Mukhil, you have any question?
Yeah, so I actually wanted to ask in this parameterized waveform, so the components, the PPE components, how do you go about extracting it from your beyond Einstein matrix?
So I'm sorry, could you repeat the question,
Oh
please?
yeah, so okay. So you told these PP parameters are like you can how do you extract them exactly from your beyond GR matrix?
Oh yeah, that's as I try to answer the other question. There is an algorithm. Once you get some, once you can calculate something like some things related to the energy of the radiated energy and some uh, things related to the orbital dynamics with using a modified gravity theory, you can map this thing. But I don't know how to tell you exactly now how could you map this your a specific theory's parameters to these parameterized Bose-Einsteinian parameters. I'm sorry, but it's
Quite long.
yeah
Yeah, it
but
takes.
there's an algorithm for that, but it's a technical thing, but it's a straightforward computation.
Okay. Also, in that EOS you showed for the DM admix neutron star, which components correspond? So that you showed the EOS for the DM admix neutron star, right? So in that, which components correspond to the DM part of the neutron star?
Wait, could you repeat the question,
Yeah. So
please?
after those, the previous equations, the dp by dr and the dm by dr equations. So in this, which components relate to the dark matter component?
Yeah, it's because thank you for the question. I forgot to mention that the I here in this, because this equation 11 here is actually two equations. So the I here is just like uh, to index the kind of the type of matter that you're concerned about, because one equation is for like baryonic matter, and then this part here is just the total, you sum the pressure of the baryonic matter and dark matter. But there is one equation like this for baryonic matter, and the other one is for dark matter.
Okay. And what does the epsilon correspond to here?
Epsilon, it's the energy density.
Okay. Thank you.
Okay, I Mukhil, if you have any questions, you can ask him later on by email. We need to conclude. So let's thank Rafael. And we will see you guys next week. Bye bye.
Then it's in person.
Thank you.
Thank you, Rafael. It was very nice.
Thank you.
Great
Bye.
notes. Very good.
I swear.